Hi, welcome back to Extreme Academy Live Part 5. These weeks are going past really quickly now. We're now into Part 5. Now, before I introduce what Isaac's going to be covering today, we had quite a lot of questions over the week and in last week's sessions about how's the exam going to work, what is the exam, how do we get access to it, stuff like that. So I thought I'd cover a few of those points now before we get going. So in week 8, we will share with you a link to where the exam is going to take place. It's going to take place within the within Extreme's learning management system. We call it the Extreme Dojo. So this is the certification exam. There is no cost for it. We'll provide you with a link. In order to get there, you'll need to register for an Extreme portal account. Now, don't go and do that yet because we're setting up a special registration site just for the Extreme Academy. So we'll share this with you in week 8. And when you get to the exam, it's going to be pretty straightforward. It's online, it's not proctored, so you can do this at any time you want. The exam is multiple choice and it'll take you about an hour, probably between 40 minutes and an hour. All the questions are multiple choice and you've got 2 attempts to pass the exam as standard. Now, if for some reason you fail twice and you want to have another go, then you just need to get in touch with us. We'll reset that and you can have another go. That's perfectly okay with us. There's no cost to try again. If you come back and ask to do it, 5th or 6th time, I think at that point we might come back to you and just see if you need some help on some specific topics before we activate the exam for you again. But we want to help you get through this exam, so we'll give you as much support as we can. Now, as soon as you've passed the exam, in the same place in the Extreme Dojo, there is an achievements tab, and in there is where you can view and download and print your certificate. And there's also a badge in there, a digital badge, which you can download. You can put that on social media, and we really encourage you to share that success and that achievement with your social network once you've passed the exam. So that was a little bit of detail about the certification exam, but don't worry about it. We'll share all of that again in week 8. And if you've got any specific questions, you can ask a question of the Extreme team in the usual place on the app, which is probably showing over my shoulder right now. So all the Extreme team are waiting for your questions in the app, and you can take some quizzes in there as well, just for a bit of fun as we go through the lesson today. Now, today Isaac is going to be covering more on wireless, the fascinating topic of wireless. That's in the first half of today's session, and then after the break, he'll be getting onto a new topic, which is about the internet. What's the fundamental operation of the internet, and what do you need to know? So he's going to be introducing you to that topic in the second half. So we're ready to go. We're ready to get into part 5. Now, I've seen Isaac a little bit earlier today when we were doing a little bit of preparation. I think he's going to be wearing his hat today, and he's got some new things on his shelf. So have a look out for what he's got on his shelf this week. So Claire, that's it from me. If you want to switch over to Isaac, let's go and do session 5.
Hi everyone. Thank you, Rowan. Thanks for that introduction. It's so great to be here again. Week 5 is where we are. We're on the way, we're over the curve. We're going down now. Week 8, as on week 8 we will open up for the exam. We'll talk a little bit about the exam and then open up, and you'll be able to get a certification if you pass the exam. That's really exciting. I'm so excited about this. I just wanted to say we've had such positive feedback. We've now got thousands of people who have signed up to attend Extreme Academy. The videos are available to them. We've had so many people watch the videos on both YouTube and on the Vimeo channels. It's been fantastic. It really has been fantastic, and I just want to say thank you. Thank you for everybody who's watched. These sessions are long, 2 hours, but so far you've sat through 4 of these sessions. That's 8 hours in total. Well done. Absolutely well done. Thanks for all the people who contribute on the on the on meeting polls, and for the people who post their questions as well on Vimeo with the chat, and not only post questions but also people who respond. Last week I was just looking through the questions and stuff, and there was a lot of you that were helping those who don't know as much, right, and ask questions, and you were just been fantastic, an absolutely fantastic community. So I wanted to say thank you, because this is what builds a community, right? When we help each other. It's not just about one person doing all the talking and nobody else being involved. It's when we help each other to learn. That's when we become community, and that's when we become powerful. I really want to encourage you. I know I've mentioned this before when we've spoken about the fact that we have a target of 50,000 people, to reach out to 50,000 people. Well, not to reach out, but hopefully to be able to train through this program 50,000 people who will then go on to become networking engineers in different capacities, being it in wiring up networks, in starting small businesses that build networks for small companies, or be it as a networking engineer in a large company. We want to inspire you. We want to get you to the point where you can have a fantastic career in this. So that's our vision, 50,000. Now, we can't do it by ourselves, because it's a big ask. 50,000 is a lot of people. But if each one of you help us, if each one of you tell a friend, tell somebody you might know, tell somebody who's unemployed, tell somebody who might have lost their job in 2020 due to COVID. If each one of you reaches out to one more, if each one tells one about this, then we can magnify the reach of these courses, of this training. We can magnify it many, many, many thousands of times. Stuff that with Extreme just by itself we can't do. So help me, help Extreme, help a friend by telling one about this, by telling somebody about this course. Encourage them. Hey, go watch. There's some interesting stuff on there. You might learn something. Who knows? You could be part of changing a life. So help us build community. Thank you to everyone. Also wanted just to say thank you to my management team. There's a whole lot of people. I mean, people like Claire, Rowan, Paul, Stuart, John, Ben, and others that Tomasz, who sit behind the scenes and enable us to be able to do things like this. People answering the live questions and stuff like that. Dave as well. It takes a lot of work to put all of this together, and as you see, it goes smoothly. It works week after week. There's a lot of stuff that goes on behind the scenes. So to those guys as well, I just wanted to say thank you very much. Now, today we're going to look at the second part of wireless. Last week we kind of did wireless, and we spoke about terminology. We spoke about things like ESSIDs and the SSIDs and server sets and what they are. And so we tried to kind of cover the very, very fundamentals of wireless without actually doing the hands-on stuff. And today it's going to be more hands-on. We start going a little bit deeper. Don't forget that course 2, this being course 1, not session 1, not session 2. I'm talking about the course 2 is going to be 2 days or probably 8 sessions of 2 hours each, just talking about wireless. Wireless is a massive topic, a really interesting topic, and I can't do it justice in these little sessions that we've done. I certainly can't cover all the technologies, but it's if you have an interest in that, and I think from the comments and stuff there's going to be a lot of people who are going to be watching, then make sure to stick around and listen around for announcements regarding the wireless course. I think it's going to be a stunner of a course. I've seen the course. We finalizing and signing off the course now. So let's get on like we normally do by going to look at the objectives, learning objectives that we have. And I'm going to read it again. This one is really easy. To understand the characteristics of Wi-Fi, right? Now, again, I can't do in one session what some people spend their lives studying, right? I just can't. This is such a deep topic. But the objective over here is to give you an overview, to whet your appetite, to pique your curiosity, so that you will go out and read more and study more and become, interested in this technology and learn more. And if I manage to do that, if we manage to do that, to get you interested in this type of technology, then we've done a really great job over here. So remember, I encourage you, don't think that you can just listen to 50 minutes of Isaac talking about wireless and know everything there is. No, there's plenty of stuff that you can go and read, books, videos to watch on YouTube, a lot of interesting stuff, even material from Extreme Networks, a lot of stuff. So read, I encourage you to read and go and learn more. So, understanding the characteristics of Wi-Fi. Okay. I have a tablet, so I just wanted to let you know, kind of like a Wacom tablet that's now sitting in front of me to help to show things on screen. In the past, when I've watched the videos back, sometimes it's not really clear what I'm trying to show, but hopefully today with the tablet it will become clearer. So like I said, the first session is going to be on wireless. The second session is going to be really quite an interesting one, because we're going to be looking at how the internet works. Now, of course, again, people spend their lives talking about this. What I'm going to be talking about really is routing, how routing happens. For example, when we know that a data packet has been sent and it leaves my black box, right? When it leaves it, we know that it's going to get to a destination, and we know it's going to cross the internet, which is a network of networks. So today we're going to try and figure out how does that actually happen in practice, right? Because there's not a long cable from my house, to the destination, to CNN.com or anything. There isn't one long cable. It's going to go through dozens, possibly, of routers to get to the final destination. So what determines which routers it goes through? And that is kind of like a GPS, right? When you say, hey, I want to go to, Cambridge, I want to go to London. How do I get to London? Well, the GPS has got options, and it chooses from all the available routes, it chooses one, and it says this is the fastest route for you to get there. We're going to talk about that on a routing side. It's a fantastic topic, and I hope that at the end of it you're going to really enjoy it and understand. Okay, so let's jump in. In the last session, we spoke about Instagram, a practical example of Instagram, what happens when I send it. And you saw how everything was converted into zeros and ones, and off it went. But wirelessly, right? We spoke about the example in Instagram. We were all using a mobile device. It's quite different to when you use a tethered device, a device with a cable. So if you're sitting in an office at the moment and you have a desktop, perhaps you have a desktop, and it's got an Ethernet cable. Well, you can kind of see from this section over here, right, that if you're sitting with an Ethernet cable, then this is what we're talking about over here, the switch. You are plugged in. Instead of an access point over here, you would have a computer, your computer, and it would be connected using an Ethernet cable into the switch, and that switch would be connected to the gateway, and that would be the equivalent of your little black box, and off it goes. But we're talking here about wireless, right? A device, a mobile device, which you are going to be using to send out that Instagram post. So the difference comes in between here and here, right? Where this part here is you connected to it using a cable, you are going from here to here wirelessly. So on a networking layer perspective, it's exactly the same way as if you were connected on a fully wired LAN. It's still going to go from application, up on the layer 1. It's still going to go to layer 2, encrypt it, do all those bits and pieces, do the translation. It's still going to go down layer 3, layer 4, UDP, TCP. So from a networking layer point of view, it is exactly the same. Okay, to get to Instagram, it's going to have to do the DNS, etc., etc., etc. Get to layer 3, it's going to figure out, this is actually not for the internal network. This Instagram server is on there. So all of that is exactly the same. But wireless layer 2 is quite different to Ethernet, right? Because it doesn't actually have a cable. We still use MAC addresses, so that kind of stuff still stays the same. Now remember, we said in the last lesson that how do you connect to a wireless network? Well, the access point, it sends out occasional beacon frames, and it says, hey, I'm here, my SSID is, ABCDE, Isaac's home network, Isaac's guest network, here I am. And when you have a mobile device, you switch it on, boom, it detects that wireless network, and if you know the password, you can connect to that. Okay, so we said that you have these beacon frames, and you also have a broadcast that your device is constantly sending out to check if there are other wireless networks in place, or alternatively to see if there's a better access point. So as you move from location to location, it will check if there's an access point with a stronger kind of signal, and if it is, it kind of connects to there, and away you go. So on the device, a frame, remember, packet becomes a frame, ready to go. It will have its proper shape, of course, because we've now taken these zeros and ones and we've converted them into electrical signals. Remember, in Ethernet, they're electrical signals. In wireless, they become these radio waves, right? We call those things we call them modulation. Okay, so you manipulate these sine waves, the frequency or the amplitude over time, and whether, to determine if we want to send a 0 or a 1. And you can see that over here, there we go. This is what we want to do. We want to send out that information. So we call that modulation. And you get different forms of modulation depending, if you want more resilient signals, etc., etc., etc. But these signals are modulated by a radio. Now, your mobile device has a radio, sometimes more than one radio, and your especially your laptop, and your access point is going to have at least one radio or more. And what do radios do? Well, some radios transmit. So if you listen, to an FM radio station, well, they'll have an antenna modulator, and it will transmit that radio signal, and a device somewhere else, like your mobile device, will receive that, right, using the antennas. Now, again, we've discussed something about antennas. If you look, if you go into London and look at high buildings, you'll always see, satellite dishes on there, microwave towers. You'll see these antennas. So you can physically see those antennas. On a mobile phone, not so much. In the old days, you could, right? In the old days, a lot of the mobile phones had little antennas, little stubby antennas sticking out of the top of that. But nowadays, they've integrated the antenna into the actual mobile device. But you'll still see them if you think about two-way radios. Generally, two-way radios will have an antenna, and they haven't quite integrated that into the actual radio. It's just, you just don't see that, right? They might be really short, but they still have antennas on them. So as long as we understand that a mobile device is also a radio, it also transmits and it receives, and your access point transmits and receives, it's a radio as well. So everything that is radio is going to be subject to interference. Okay, I mean, you see it when you get in a car and you drive. You know, you switch on the radio, Cambridge FM, you drive, and I drive 30 miles out and I start to hear a lot of, you know, static, a lot of, you know, interference on the radio. And either I adjust a little bit to see if it gets better, but after a while, lots of interference, and it kind of becomes a nuisance and I don't want to listen to it anymore. Does that mean that the radio stops, that radio wave dies at that point in time? Not really, because radio waves really go on forever, right? A radio, you know, when a radio wave goes out, it just keeps going on for forever. It just gets progressively weaker and weaker and weaker. And if you wanted to receive it, you would need to have a really powerful receiver to be able to get that signal. Now think about that. That's what happens, right? If you think about the International Space Station, it's sitting, you know, thousands of miles away above us, floating somewhere above us. How do we communicate? We communicate using radio. It's moving at an incredible speed, but there are Earth stations that receive those signals. So even though they might be weak, takes quite a while to get there. You know, you probably couldn't pick up that signal using a mobile phone. Maybe you can. I've never tried. I don't know. But there will be transmitters that will pick these up. You think about astronomy, and you have these massive dishes, you know, listening to signals coming from outer space. Why are they so big? Because they need to be super sensitive to receive, you know, light, or to receive, for example, these radio signals that are being beamed, you know, or just appearing from outer space. So you get the idea, right? There's always going to be interference, okay? Interference. I've even seen it here in the UK with a satellite dish. We're watching television using a satellite dish, and if there's a bad thunderstorm, there would be so much interference that you'd actually lose the signal. So in Wi-Fi, it's exactly the same. Here, for example, on this particular slide, you can see this interference over here. Now, remember we spoke in the last session about the different bands. This one is a 2.4 gigahertz band, and microwaves ovens emit radiation in this particular band, right? Because they use radio frequency to heat up the molecules in the food, and it stimulates those molecules. They get heated up, and that's how your food gets cooked. Okay, so I mean, it's not going to fry you. That's why, you know, you can't press a start button if the door is not closed. You know, so they safe and stuff like that. But inside, that's what's happening. But depending on the insulation quality and the age of the microwave, you might find that if you have an access point close to a microwave and someone wants to do cooking, you're going to lose your Wi-Fi signal. It's not going to work really that well because of interference, right? And it's not the only thing. There's lots of things that cause interference. Now, one of the things that we've spoken about it might have been session 1 or session 2, was we spoke about the measurement of data, and we spoke about things like megabytes and megabits and kilobits, for example, and then we added a PS to the end of that, per second, and then we spoke about bandwidth, and we spoke about, you know, it's bandwidth per second. And there was a really great question that came out last week about that, about, you know, what equipment do you need? Do you need different equipment to have higher bandwidth? So no, you don't. If I sign up for a 30 meg bandwidth from the local ISP, I will pay an amount for that 30 meg. If I say, well, I'm prepared to pay another £5 to get 60 megabit per second, I don't have to go and change all my infrastructure because of that, because all they're doing is they're just giving me more lanes, more highway lanes where the data can come through, where more data can come through, because there are more lanes, right? So that was the PS per second. And just like bandwidth, when it comes to wireless, there is also a certain amount, a terminology and a way to measure wireless signal. Now, what are we talking about? We're talking about signal strength, okay, signal power. So just like a bandwidth capacity, we have a measurement used to determine the strength of these radio waves. And we do it on a logarithmic scale. And we use the term dBm, dBm to talk about it, and it's a ratio. It's written as small d, uppercase B, and then lowercase m. So if we use the linear scale to do it, that would be problematic, because we would be dealing with terms that are less than a picowatt, right? And we would need to write these things as 0.00000. It just would make no sense. So to find a better way to do this, we use dBm, this particular ratio called dBm. And on this table over here, you can see some of these values, right? 1 milliwatt. 1 milliwatt equals, or is the equivalent of 0 dBm. So 1 milliwatt is 0 dBm. 1 watt is 30 dBm of power. Okay. And here you can see this is really the interesting over here, because take a look at this, and let's look at this over here. Let's look at this signal, this part first. So the ratio is of the received signal to 1 milliwatt of power. So if the signal is greater than 1 milliwatt, then you will see us write the dBm value with a plus in front of it, or sometimes we leave out the plus. But if the signal is less than 1 milliwatt, then we normally write it with a minus dBm next to that. Now that can be a little bit confusing, okay, but it's important that we get, because if we use the linear scale, because the numbers are so infinitesimally small, it would be a nightmare to write this. So we use a logarithmic scale to make it easier to deal with these numbers which happen to be so small. So this is really important for us to understand. And then there's a rule that is very important. We call that the rules of 3s and 10s. Now this is interesting, and you have to get this, because this might appear in the exam. Okay, and what does this rule say? The rule says a 3 dBm gain doubles the power. So a gain of 3 dBm doubles the power, and a loss of 3 dBm, the power is halved. And let's look at that in this example over here. Look at this, okay? Minus 30 dBm, right? Minus 30 dBm gives us 1 microwatt, okay? I think that's what it is. But if you up that by 3 dBm, what do? You double it. Okay, so if you up it, yeah, the power is doubled. So we were at minus 30. We were at minus 30. We upped it by by 3. What happens? We doubled the power. And look at this over here. So this is an important rule. 10 dBm gain, the power is increased by 10 times. Do you see that? So it's not like, oh, you go from here to here, it's not like that. A 10 dBm, the power is increased by 10 times. And look at that over here, right? So 10 dBm, yes, we gain 10 dBm, all right? So we said over here, 10 dBm gain equals power increased by 10 times. So there we go. We go from 10 dBm, we add another 10 dBm, just a gain of 10 dBm, and look what happens there. We go up by a factor of 10 times. So always remember that that's really important. This rule of threes and tens. It's not this straight linear, you double here, you double. It doesn't quite work like that. So that's interesting to understand. Then what about a signal to noise ratio? You'll sometimes see this as written as SNR, signal to noise ratio. This is also important, and I like this explanation over here. It's like teaching in a primary school. I've taught classes of children, right? And it's very difficult to keep a bunch of kids quiet for anything beyond 5 or 10 minutes. Then the questions are, and if there's a lot of background noise, what does a teacher need to do? The teacher, if they continue talking at the same level, what will happen is their voice will get drowned out because there is too much background noise. If you live in near a very busy road, you will know that in the morning when you wake up or whatever, there's a lot of background noise, signal to noise ratio, right? But in the evening, the road might be dead, and so you don't have to speak as loud. You don't have to have your television as loud. Why? Because the signal to noise ratio has been adjusted, okay? The signal to noise ratio has been adjusted. So if you have a lot of signal to noise ratio, then that could be a problem, right? Because it would mean that there's a lot of noise in the background. So you would need to do a few things to mitigate that. If there was a lot of noise, then you would need to move closer to your AP, for example. You might need to increase the power level, the antenna gain. Okay, by default these might be set to 12 dBm, for example. You might need to increase that to 13 or 14, correct, to get a stronger signal. You might have obstructions in the way that you might need to move out. So there's a number of different things, and there's measurements that you can use, tools that you can use to measure these signal to noise ratios. On the Mac, there's a shortcut that when you click on I think you use Shift and you click on the little wireless signal, and it shows you all of that information. So typical Wi-Fi signal would be between -10 to -70 dBm. The typical noise floor would be -80 to -100 dBm. So you need to consider these things as well. What other things can cause interference? Well, we've already spoken about microwave ovens. They especially the older ones, they create interference on the 2.4 gigahertz spectrum. Bluetooth devices, right? Bluetooth devices create interference as well on the 2.4. And that's why we say, if you have a reasonably modern mobile phone, and I'm saying by modern, I mean, 3-4 years old, that's already what we would call reasonably modern, then they should have the ability to transmit on 5 gigahertz, okay? And that's really great. And if your wireless access point at home is also reasonably new, in fact, even if it's a little bit old, it should also be able to transmit on the 5 gigahertz frequency. So if you have a lot of interference at home, you move from one location to the other, and your signal dies on the 2.4. If you have a lot of Bluetooth devices, a lot of microwave oven, baby monitors, a lot of devices, a lot of radio devices, why don't you try changing it to 5 gigahertz? Where would you change it? Well, on your little black box, if you know how to log in, then you'd probably need a laptop, an Ethernet cable to log into that black box. You might be able to do it wirelessly as well. And you go look then at the radios. They normally have 2 radios, a 2.4 and a 5. And you might decide you'd like to try switch off the 2.4. And by doing that, you turn on the 5, and your device will now connect over 5. Of course, there are devices older devices that might suddenly stop working, and that could be problematic. Okay, if they stop working because they might just not support it. There's still a lot of these old type of devices that don't support it. An Apple Watch, for example, talks on the 2.4 gigahertz spectrum, so it doesn't talk on 5, for example. So that's just one of those things that you need to consider. But interference are caused by a lot of different things, and more interference, what will happen? The more packet loss. So if I'm trying to talk to a class and everyone is talking, I might have to repeat myself a few times. And if I have to repeat myself, then it means there's less time to explain things, because I have to keep quiet. And that's exactly the same thing that happens on wireless. If there's a lot of interference, it's a broadcast domain, there's a lot of noise, that it's not getting through. Those checksums are failing, and please repeat, right? You get lower data rates. And so the devices will know if it's struggling a lot, hey, even though I have a high capacity, I might need to scale down just to get a more reliable connection. So those are some of the things. The other thing you hear people say, oh, my wireless is so slow, I don't understand it. I bought this access point, it's got a massive capacity and all sorts of stuff, but it doesn't quite work, it's so slow. Well, Wi-Fi, the PHY layer, that layer 1 is complex, right? Radio is complex, and it's complex in nature, and a lot of things can afford it. The biggest of those is a collision domain. Now, if you remember, I think it was in lesson 2, we started to talk, or maybe 1, where we started to talk about collision domains, and we were saying things like, hey, before a station can transmit, it needs to check that, that it's clear to transmit. Can I step onto that road? Yes. I look left, I look right, there's no traffic. I can step onto the road and try walk across. But somewhere else, someone could also be, trying to cross that road at the same time. And so if that were to happen, both stations need to go back and wait as a random set of time before they try and transmit again. Well, in wireless, the whole wireless spectrum within your home or your access point, all of that is a collision domain. Okay, and so there would be tons of devices in your home. Think about it: iPads, iPhones, microwave oven, Bluetooth devices, baby monitors. All of that is one big collision domain. So if all of these devices need to do ARP requests and things like that, then there's going to be a lot of noise, okay, a lot of broadcasts on them. And because when a broadcast happens, everyone needs to listen. Imagine if you have lots of broadcasts happening, it's going to be slower than it's going to be if you got a physical connection. That's just the nature of wireless, and it's going to get worse, especially at longer distances, right? The further you are away from the access point, it's like, oh, I didn't get. Can you repeat? Oh, there's a broadcast. Oh, let me handle this. Oh, yeah. That's why we talk about wireless can sometimes be slower, or is often slower than a physical connection. The best connection that you can have is a physical connection, right? So it's a toss-up all the time, and if your access point and your device, if they've got to make the judgment, they will prefer more reliable than faster. That makes perfect sense, right? If they try and connect at the high speed and it's not working, they'll step down. Why? Because reliability is more important than just pure speed. What's the purpose of having pure speed if there's just so many repeats and broadcasts because it didn't get through, the information was unreliable, didn't get through. So another reason that we have slowness and stuff like that, people say it's slow, is attenuation. And this could come through absorption or just attenuation as well. So you would know that if I were to place a towel, a bathing towel in front of my face over here and chat, then that towel would absorb some of that. In fact, I have an audio towel absorption tile, I suppose, in front of me that I use so that the voice in my office doesn't reflect. That's what it looks like. And what actually happens with this? Well, I put it in front of me, and when I chat, the voice, those radio waves that are coming out, that tile in front of me prevents and absorbs some of those waves so that they don't go through and it sounds like I'm talking in an echo chamber, okay? Because it's radio. It's radio. It's radio waves. It's wave sound or audio audio waves that are being broadcast as I talk. And so when a AP or a device or your mobile phone broadcasts some things in your house, in your office, are going to absorb some of this. It's radio frequency that's been transmitted, and it penetrates lots of things. I mean, you put a pane of glass, radio will go through that pane of glass, but some of it will be absorbed. And then there's attenuation. So within a particular medium, there's always going to be a loss of signal strength, right? So if you're in water, there's going to be a loss of signal strength. That's always going to be a natural phenomenon of radio frequency. There's also a phenomenon known as free space path loss. And what do we mean by that? Well, look at the first part of that phrase, free space. So your house, inside your house, is not free space. It's got walls, sometimes made of partitioning, other times made of glass. You might have a glass wall or brick or concrete or rock or wood, for example. Those are all mediums, but they're not free space. Okay, it's not free space. But if you were to go outside into your garden and put a AP there, then you can already imagine that there's less things that will absorb sound. Attenuation, there's going to be less things there. Go to a football field or a rugby field, and you can see that there's going to be a lot more free space. But that doesn't mean that there isn't a loss. There is a loss associated with free space. And here's the formula. We call it the inverse square law. And it means the power is decreased 4 times or 6 dBm every time the distance gets doubled. Okay? So every time, the distance here is measured in R. So when the distance is doubled from R to 2R, you'll see over here, you might not be able to see it that clearly, but over here in yellow, in dark yellow, there's an A. Okay, there's an A, right? And you can see there's the source, the antenna, and it broadcasts this radio signal, okay? At R, it has a particular strength. At 2R, right, it decreases the strength 4 times by 6 dBm every time the distance gets doubled. So from there, the distance gets doubled. What happens? Again, it halves that distance, and that's just physics, okay? That's just physics. There's nothing you can do about it. That's just physics. You get the magic of talking to the International Space Station? Yeah, did you get it? Look at the distance. Look at the distance. It halves, or the power is decreased every time the distance gets doubled. Indoors, that exponent might give you a value of between 2 and 6. So here we say practically, wireless range indoors can be about 1/3 to 1/10 of what it is outdoors. Why? Because of all the things that you have in your house that absorb signal strength. here you can see the amplitude. Yes, dBm, there's an access point, and you see the distance, right? As the distance changes, you'll see that the power of that radio frequency drops. You have attenuation, for example, a wall. When the signal hits the wall, while it's in the wall, it's going to drop, right? It's going to happen. That's the nature of it. And so it goes in at a level, it comes out at a weaker level. And in XIQ, which we're going to do a demo of for you, not today, but we're going to do it, when you place an access point, here it is, this thing that says SIM, when you place an access point, what happens? It shows you the signal strength, and you can see the orange, that orange color there, that's where that signal strength is the strongest. But as you go away, look at the attenuation. When you hit the wall, you see that it changes, right? Because the wall is going to absorb some of that. There we go, free space path loss. There's nothing over here. So as you go further and further away, where there's free space, that's what happens. So let's now look at an illustration, an animation that you can see over here. You can see that right at that access point, it might really close 54 megabit per second. Wow, that's fantastic. If that's what you've got in your house, a number of people, that's fantastic. But as you move away, what happens? There's this concept of data rate shifting. Your device sees that signal strength is not that long, or that strong. It starts to, well, we better talk a little bit louder, to try and keep that signal strength, because it's not that good. And so I might start talking slower. Okay, I might start, are you getting what I'm saying? Yeah, you're talking too fast. Slow down. And this is what these devices will do. They will shift their data rates. So when people say, oh, it's wireless, it's slow, etc., these are some of the explanations as to why. If there's a lot of noise, a lot of interference, if you're far away, well, I might need to do a retransmission because I didn't quite get that. Okay, so what about the real world speed versus the real speed? And we kind of just touched about this here. But you can go to a place like these stores that sell access points, right? And you'll see advertised, this does, I don't know, 1,750 megabit per second, and you think, oh, that's absolutely fantastic. This is what I can get 1,000. Think about it, right? Think about it. What's the point of getting 1,750 megabit per second access point when you've only got a 20 meg connection to your house? So you can talk really fast to the access point, but the access point is connected to that black box or whatever, and you're only getting 30 meg per second. But what does it mean when people say things like, oh, this device has a capacity of 1,750 megabit per second? Well, if you look carefully, you'll read the small print. This is what we're talking about, right? We're talking about 450 megabit per second on the 2.4 gigahertz and 1,300 megabit per second on 5. So I'll say, on 5 gigahertz, this is the capacity that it can handle. And on 2.4, this is the capacity that it can handle. That's what they say to you. But they also, you need to consider things like that some of these access points, for example, this particular one, might have what they call 3x3 MIMO. MIMO would mean multiple input, multiple output. It's a technique to multiply the number of antennas for transmitting and receiving. So it's kind of like bandwidth. If you've got a wide highway, you can transmit more data. If it's narrow, you can transmit less data. So they have this technique that's designed exactly for this. Each transmitter can transmit its own portion of data and receive its own portion of data, and they can do this across multiple antennas. That's really great, but not all devices have the ability to do this. Most mobile devices only have 1x1. They don't have 3x3. Okay, so they can only receive and send on one radio. They don't have 3 radios. And you might say, well, why don't they have? If the access point has 3 here, why doesn't my mobile device? And one of the answers to that would be, Well, you would probably want to have a battery life that's more than 20 minutes, right? More radios you have, more transmission, there goes your battery life. So these are kind of trade-offs that would need to happen. That device that advertises all of that speed might support 80 megahertz channels, so these wide channels. But most laptops will only support 40 or 20. So even though this access point has incredible capacities, to really use a lot of that, your device would have to be up to spec to use that. And it's not, because your mobile phone doesn't do those types of have that type of functionality. So when they talk about these functions and all of this, what they're really talking about is capacity, right? This 6-lane highway can take 50,000 cars per hour. Yes, it can. Yeah. But not on a Monday morning or on a Friday afternoon. It could still take that, but then they're driving at 5 kilometers per second. So you got the idea behind that, okay? So in wireless, we've spoken about this collision domain, okay? And because there's so many retransmissions, it's just a nature of physics on wireless, then we say that the throughput, because of all the overhead associated with wireless and the retransmissions and things, that the data rate, actual data that's being transmitted is about 50 to 75% of what is possible. And that's just because of all the overhead that happens. The broadcasts, the beacon frames, all of those things that are happening on wireless. So there's no ways that wireless can ever be as efficient as having a physical cable. So if you're in the design environment and you need to shift massive video files or massive Photoshop files around the office, 300, 400, 500 mega gig Photoshop files around the office, if you have a desktop or even a laptop, you'd be better served having an Ethernet connection of a gigabit rather than trying to do that over wireless, because over wireless it's going to be much slower and you're going to kill it for all your other colleagues who just want to do the normal stuff, right? You always see this. You go to an airport or an airport lounge, you're sitting in the airport lounge, and there's always got to be some guy who wants to do a Windows update in the airport lounge and kill the wireless for everybody in that lounge. Don't be that guy, right? Don't be that guy. So the advertised speed is 1750, but actually, that only if you're on 5 gig and you're using the full 2.7 gig, and then you've got attenuation, and you've got absorption, and you've got overhead, and you've got, yeah, sure. How do we maintain connections, right? Look at that slide. Look what's happening there. Look at that animation. I'm on a campus. I'm on campus A. I've got my mobile phone. I'm connected. I'm uploading a file. I move to campus B, campus C, campus D, and my connection just goes all the way through. How does that happen? It's kind of a little bit like magic, right? Well, wireless uses roaming mechanisms. That's part of this overhead, that wired connections don't have, and why we say, between 50 to 75% is what you get in the data rate, just because of all the overhead. This is one of those overheads, right? These roaming mechanisms. So when a device roams from access point to access point across an office, across an airport, across a venue, a concert hall, you go from a stadium, for example, go from location to location, and you keep having your wireless. What is happening there? Well, you have these roaming mechanisms, and as you go closer to an access point, your device says, hey, that access point is now closer. I have a stronger access signal from this access point than the one I was connected to. And the access points they talk to each other. They pass information to each other, such as MAC addresses, encryption keys, etc. They do this in the background. So you join a wireless next, and it shares its information with the access points next to it. So you move to the other one, and the data is already there. When you get to this one, it shares it with the next one. And so it's magic. It's seamless, right? You go from one to the next, and it's uninterrupted. You don't have to, it's the same wireless network. You don't have to reissue your password, and it's just seamless. That's because of all this magic that's happening in the background. These beacons, these frames, this advertising, this noise that's happening in the background saying, hey, stronger signal here, connect to me, I'm stronger than, and your device connects, and it's seamless. It works absolutely fantastic. Now, people have often said, gee whiz, on Wi-Fi, my signal, my battery really gets eaten a lot on Wi-Fi. I kind of felt that it's not always like that. Sometimes on mobile, when I roam on mobile, especially when I travel, I found my battery goes a lot quicker. But nevertheless, whether I'm on wireless or using the cellular radio, it's still a radio, right? So why would a battery get depleted a lot quicker with this? Well, then if I turn off, like you get on a plane, they ask you to go into airplane mode, and if you go into airplane mode, okay, you don't have wireless at all, but if you go into airplane mode, you find your battery suddenly lasts 15 hours. Like, gee whiz, how did that happen? Well, you're not doing broadcasts. You're not doing multicasts. There's no need for the retransmission. There's no need for, stepping these different data rates, faster, slower. Oh, I don't hear. Think about that, right? When you go into low power mode. I couldn't hear what you said. When you go into low power mode, what happens? Well, you don't have these radios doing everything that you needed to do in the background. Oh, that was really funny. But so that would be one of the reasons, right? When you switch on the radio, there's broadcasts, there's multicasts, there's all of these things that are happening. Also, access points, remember we said they do these beacon frames, but they also do ARP and these broadcasts. And every time it does a broadcast, what happens? Every device on that network, on that wireless domain, SSID, has to wake up. So your device could be sleeping, could be sitting there doing nothing, but your access point is going ding, 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 ding constantly, and it's constantly waking up your device. So these are things that can lead to your battery life suffering, right, as compared to when you go into airplane mode. Lots of interference. So we've spoken about that before. You get lots of interference. If you get it, a lot of signal to noise ratio, a lot of noise floor noise. What happens? If there's a lot of noise, I have to say that again, repeat that again. All of that uses battery. And a lot of that can be fixed by clever wireless LAN design. Remember, we talk about designing networks. If you think about these things, when you understand these things, then the way you design a network is important. Where you place your access points becomes really important. And roaming, okay? You roam, as you roam, if you roam a lot, then of course it's going to use wireless a lot. And you've seen this, for example, if you're in your car and you have your GPS on, and you're receiving, you might be on a Bluetooth headset, etc. Well, what's going on? As you go from tower to tower, you're having this handoff from one to the other. And that's all eating up your battery. And you see, if you do a car trip and you don't plug in your phone, you will see that it'll be depleted. The battery will be depleted that much quicker. Why? Because of all the activity that's going on in the radio on the background. So I hope that this has been useful to you. It's not a deep dive. If you're an expert on Wi-Fi, this hasn't answered your question. It's not about that. But hopefully you begin to understand about wireless It's just radio, how it works on an access point, how the back end is exactly the same, as with an Ethernet connection, but the front, because it's radio, more overhead, a lot more traffic, a lot more noise, not as efficient. Now you start to understand the reasons why. That even though that box is advertised as being capable of whatever it is, in reality it's never quite as much. So hopefully it's been great for you. I'll see you on the other side of these this break. Take 10 minutes. We'll have some ads and we'll have some stuff on here. Cheers. Bye.
We're a community mental health agency, not-for-profit, based in north central Indiana, and we're rapidly growing throughout the state of Indiana. When I first started at Bowen 7 years ago, we were somewhere around 700 employees. In those last 7 years, we've grown to almost 1,300 employees now. One of the challenges with an organization that was scaling as quickly as Bowen was being able to scale within IT in that same capacity, and we've been able to do that because of Extreme. We needed a partner. We needed somebody that could work with us hand in hand as we designed and continue to make improvements to our network, and Extreme fit that better than any vendors that we looked at. We feel comfortable knowing that Extreme is leading so many different technology pieces that it's a partner that we feel like we can have for the long haul. The massive customers that Extreme has that can handle the types of wireless capacity that it takes to maintain a stadium, we feel confident that that is going to bode well for our offices. One of the things that makes Bowen Center such a leader in our industry is the way that we're able to provide telehealth with our clients. And we're able to utilize telehealth systems to put doctors in front of clients and clients in front of doctors. With that, we need a solution that is A, reliable, and B, secure. And Extreme has done so much to ensure that that happens, and they're changing lives because of it.
SUNY Canton is a small institution in northern New York. We have approximately 3,200 FTE students, approximately 450 faculty and staff, and the campus itself covers approximately 500 acres. The network infrastructure is the foundation of everything we do. We've talked about online student engagement, our esports initiatives, our live streaming efforts. Everything that we do on campus relies on that critical infrastructure, and Extreme has been able to provide that and provide the support from design to rollout to support. We currently have one IT staff member that manages the entire network. Overall, our organization is fairly small. We only have 18 full-time employees. At any given time, about 4,000 people on the network. That varies throughout the year because we have a large summer and winter term. Each user typically has 4 to 5 devices, so we do see a significant volume of devices on our campus network. We had an aging infrastructure, and we had a need for additional bandwidth and additional Wi-Fi coverage on our campus, and those were the primary drivers into us moving towards a full campus-wide upgrade. Since we deployed Extreme, we've had the ability to better manage our network from a security standpoint, and also allow more access to personal and Internet of Things devices across campus.
Esports is the competitive experience of playing video games. So much like we would play baseball or football in an arena, we play our sports online in virtual battlefields or virtual arenas. Esports has grown to become a multi-billion-dollar industry across the world, with the majority of the players coming from East Asia. However, the strongest game market being in the Western Hemisphere, United States.
Extreme has done a terrific job in helping SUNY Canton grow its esports team and get our name out there. So it's been a great partnership for us. They've helped us with our marketing, and we've partnered with them on a number of different initiatives that have went really well and gotten SUNY Canton's name out there, helped us build our reputation in esports. So Extreme has just been a wonderful partner, and we couldn't thank them enough for helping us really get things rolling over the last year and a half. We are a mix of students both on campus and online. And so that was one of the reasons why we decided to start an esports team, is we wanted to give our online students the opportunity to participate in athletics as well. If you take a look at what traditional athletics brings to a school, esports brings pretty much all of that as well. So they do better in the classroom, they have higher retention rates, they have higher graduation rates. The students seem to be more fulfilled. They are with a group of students who have similar interests. Esports has dramatically helped our enrollment and our retention numbers. Students come here, they want to play esports, and they want to be involved.
Extreme Networks GTAC support has been fantastic. In my opinion, it should be an industry standard. Our local engineers and account reps have been fantastic, available virtually 24/7. I can't speak highly enough about the folks at Extreme that I've dealt with, and I think that's the differentiator between other technology vendors and Extreme Networks. For us here at SUNY Canton, Extreme Networks has been the right choice.
And here we go. Here we go again. Hope you had a nice break. So someone asked if I'm broadcasting from Cambridge again today. Yes, I am broadcasting from Cambridge, incidentally, the home of Charles Babbage, who was quite a unique individual. He was a polymath, and he's one of the guys who was so clever at mathematics that they gave him a degree without him writing an exam. Charles Babbage. He's some call him the father of computers. Interesting. Go look him up. Interesting person. All from the wonderful city of Cambridge. Okay, so the second session then today that we're gonna get busy with is we're going to look a little bit at the internet, right? The internet. Try and demystify the internet a little bit. We've said before that the internet really is a network of networks. I think that's one of the best definitions, right? It's just a network of networks. But how does it work? We kind of now have seen how networks work internally, be they wireless or wired. We've used the OSI model to understand what actually happens behind the scene, how these things are packaged. Data is packaged into packets and then into frames, and the addresses of the gateways and the MAC addresses for internal. So we kind of seen all of that, and that's really interesting. But once it hits that black box, right, it's going to have the black box has two addresses. It's got an address which is its internal address, its gateway address, right? And everything that needs to go out is going to go to that gateway. And then, of course, it's got an external address, right? This is important to understand. It has an internal address, and then it has an external address as well. And that is to connect that device to the internet. Now we know I'm sitting here in Cambridge, and if I want to send something to Claire, and Claire is in Reading, we know that there isn't a cable that runs directly from my computer to Claire's computer. Kind of, we know that, right? Just like there isn't a cable that runs from here to the International Space Station or anywhere else. It's going to go through a number of different routers before it gets to Claire, right? It could be 5, 10, 20, 100 different routers. I don't know. But the technology is going to allow the data frame to get from my computer to its destination by going through a number of different routers, and they in turn will route the traffic to the best possible route, very much like GPS works. But before we get into that, let's look again at the learning objectives. So what we're going to be doing here is to learn how TCP IP communication is used for typical client-server connections across the internet. To understand a little bit about internet protocols, a little bit more about internet protocols that make up that TCP IP protocol stack, and then to understand an important protocol called ICMP. All right, ICMP. A little bit more about it and how we can use this, and engineers and techies, we use this protocol to diagnose network connectivity issues. When somebody says oh, the network's not working, this would be one of the first protocols that we would use. And when I say protocols, a tool, we use a tool that uses this particular protocol to diagnose these types of issues. And then we're going to learn a little bit more about LAN to internet operations, such as we're going to talk about NAT and www, the World Wide Web, and DNS and stuff like that. So there's a couple of really interesting topics that are coming up within the next 45 minutes. Stay tuned, stay focused. This is good stuff. Right, let's get some government juice. Okay, so internet, global network that theoretically at least allows any kind of traffic to pass freely from one place to another, and thus enabling services and human activity, etc. What do we mean we say theoretically allows any kind of traffic? Well, if nobody fiddles with it, then all type of traffic should be able to traverse the internet. But that's not always the case. Everybody knows that the Great Wall of China is a physical wall, but they also have a massive firewall in China. So in the sense, the Chinese government kind of puts up an artificial barrier to this statement that any type of traffic, the Chinese government might say that, hey, we don't want this type of traffic to come into China. Okay, and so they might block it. So this is all that I mean by the statement, that theoretically all type of traffic, anything, any media, any file should be able to traverse and go anywhere across the internet. Theoretically. In practice, it might always not be the case, and sometimes there are valid reasons for that, and sometimes they aren't. But that's kind of what we mean by that. They say that by the end of 2018, there was something like 22 billion devices connected to the internet. That's 22 billion. When you consider that you might have 7 billion humans on Earth, think about 22 billion. That's 3 times as many devices connected to the internet. That's incredible. But where will it be in 10 years or 20 years time? Double, triple, quadruple that amount? Very possibly. We don't know. With the growth of IoT, it is very well possible. But in this image that we have on the screen, let me just go back over here and let me see if I can switch to the laser. Let's go. Oops. Why does that not work? Oh dear. Okay, so let's go here and let's go laser. Okay, there we go. So metropolitan area networks, we've spoken a little bit about that. We've spoken about local area networks, right? Data centers, corporate lands, right? Corporate lands. We've spoken about campus networks. You can see that, in your home office, you could be connected to the internet, and you could see in this image over here hundreds, thousands of connections across the internet that link up everything. That's one of the beauties, the great beauties about the internet, is that because there are so many multiple connections going to every point, there isn't a single point of failure. And that's a fantastic thing, right? There isn't one single point that if you knock that out, the whole internet grinds to a halt. No. Even when you had the 9/11 attacks in New York many years ago, I remember in South Africa watching in horror when the attack that took place, and we could still get onto the internet. What we did notice was everything took longer. Why? Well, because traffic was being rerouted, and of course everybody wanted to watch and see what was going on. Although at that time, more people probably watched events on television than watch necessarily on a computer screen or a mobile device. But you get the point, right? There isn't a single point of failure because, like a spider web, there are so many different links that if one goes down, well, the traffic basically reroutes through something else. It's a fantastic system. Right. So let's understand a little bit more about how these things work, because we've spoken about the fact that routers, there's lots and lots of routers across the internet, and they route the traffic to the best location. And although that's a true statement, like, how do they do that? Because you can't just have a router. You can't just have a router that just sits in outer space, hanging off somewhere. It doesn't quite work like that. All these routers belong to organizations, belong to companies connected onto the global internet, right? And so they will go from this company's, router to another company's router to another organization's router to another. Do you understand? So these routers have to kind of be connected into systems and owned by companies. And what we call these things is we call them autonomous systems. Autonomous systems. So the internet, in its simplest form, we could call it a collection, a bucket, right, of autonomous systems. Now, what is an autonomous system? Well, it's a small portion of the internet. You can think about the UK, the internet infrastructure within the UK being an autonomous system, or put it this way, slightly differently, having many organizations within the UK and each one of them being an autonomous system. So I'll give you an example. My ISP in Cambridge is BT, right? British Telecom. Now they operate from the north to the south. They operate all over the UK, and they have hundreds of probably millions of customers, right? They have infrastructure that reaches all over the UK, right? Routers, systems, servers, mail servers, web servers, DNS servers. All of this infrastructure that they have is connected together into this organization called British Telecom. It could be Verizon. You could be in the UK, Vodafone. Think about your your mobile phone provider. They would be an autonomous system. IBM would be an autonomous system. Extreme Networks would be an autonomous system. Big organizations, O2 and all of these providers, they would be autonomous systems, described as autonomous systems, but they have other things about them, right? So they have this infrastructure which contains all this structure that I told you about, this the fiber and the links and all of this stuff. Of course, they also have you as customers, and you have devices, right? Computers, tablets, mobile phones. You have all of these. So as a customer of BT, this autonomous system of theirs encompasses end-to-end everything to give you internet access. And when you send an email, when you try and browse to a website like extremenetworks.com, it's going to use BT's autonomous system, and from there it will go to someone else's autonomous system, until eventually it gets to Extreme's autonomous system, right? Extreme Networks, or maybe the provider, the ISP on which Extreme Networks sits. Okay? And so you have these autonomous systems. They are worldwide. They operate in every country in the world. Now, who controls them? Well, we know that ICANN.org, they are an organization, an umbrella body that controls they control the oversight of the internet. And under ICANN, you have a whole lot of different bodies that control different parts of the internet. It's really a miracle, the fact that it actually works. One of these bodies is called IANA, that you see on the screen over there, IANA, right? IANA. And they are the body that does things like delegate IP addresses or ranges of addresses to specific countries, and within those countries they allocate them to registries. So Vodafone might come and say, listen, we're going to start a new business and we need 10,000 IP addresses. Well, they would go to a UK body, a registry that would have addresses allocated to them, to the country, by IANA. They would have block of addresses, and so you could query IANA. So where does this address come from? If there's a company called MaxMind, MaxMind, and they've made a business about linking an IP address to a location. So you can go onto MaxMind's website, type in an IP address, and it will tell you where the country where that IP address is registered to. And if you pay them money, it will tell you, well, it's not only in that country, but it's that ISP. And if you pay them more, they will say, well, it's in that country, that ISP, and it's in the city of Cambridge. And if you pay them more, well, it's in that city of Cambridge, and it's in the village of Impington or Histon or whatever. So they make it their business to know where an IP address is located. So, but IANA is the body, the worldwide body that controls all of that information. And so if you were an autonomous system, you would get a number. You would register and ask IANA to give you an autonomous system number, and it looks like this that you see on the screen. So this particular company over here is an autonomous system, right? And they have a registration number. 12000012. That's the autonomous system number. So they could be, like I say, generally big players, not the small little player, not your small little company, big players, like your BT Telecom, right? The fact that there's a lot of them makes it easier to manage the internet, right? Because there's not one single body that is in control of every router around the world. No, all of these companies, they control and manage their own routers. So it's easier in that sense. There's, like we said, there's no single point of failure. And so they might have slightly different rules and regulations about how their autonomous system is. So BT might say, well, as a customer of BT, you have to use this, and these are the rules. In Verizon might say, well, we have a slightly different set of rules. But at the end of the day, they can't do anything to break the internet. They can't do anything that stops traffic flowing from one location to the other. They have to use common languages, common protocols, etc., etc. So if we're good on that, then we need to understand then that between all of these autonomous systems, there needs to be connectivity, right? Because that's what the internet is about. It's going from if I said no, I only want customers from BT to come on to get onto the internet, nobody else, well, that's a real problem. Because if I wanted to browse IBM's site or Extreme Network site, they're not BT customer. Like, no, the internet is open, and we must be able to get to anywhere and any location that we want to do. So the internet is not just about connecting servers and computers, so that we can browse to a particular website. There's all kinds of devices that are connected to the internet. Nowadays, your fridge can be connected. Your thermostat at home can be connected. IoT devices, weather sensors can be connected to the internet. It's so much more. And so these systems have to be able to connect to each other so that the information that we need can be fed back to us. Radio stations, television stations, so many devices. This is kind of a map on the left hand side. Someone tried to map out what the internet looks like, and you can see it's I mean it's amazing. If you take one of these over here and you expand that out, just look at what that might look like. And that might be just in a local city. That might just be in Cambridge, for example. But it's a network of networks. Incredible. And this over here is showing you the submarine cables. These are the cables that connect all these continents together. It's absolutely amazing how look at all these cables coming down to Cape Town in South Africa, coming down the border of Africa, and as they come down Africa over here, they break out into all of these different countries, and look how they link up the world. The entire world is linked up with these cables underwater, big, thick, heavy cables that are dropped onto the bed of the ocean and laid many, many thousands of kilometers, carrying fiber optic cable, right? Encased glass, but encased in massive cables, so that they they don't easily break, and occasionally they do break. So the internet is so big that it would be absolutely impossible to try and have a static route for the way that traffic should flow. So if I'm in South Africa and I want to browse, go to a website, send an email to somebody here in the UK, what is the route, right? You couldn't have a single static route, because again, if the route goes down, you just lose connection? No, you can't. So you have to have, they had to, when they designed the internet and started thinking about these, you needed to have a system of dynamic routing. So if a link goes down, then another one takes off and gives you that section. But you had other things that you needed to do as well. You had to create all this infrastructure that is in place. Underlies a fundamental question that needs to be answered, and that is, what is the shortest route? If I'm in South Africa, if I call my mom in South Africa using FaceTime, the routing protocols are determined to do one thing, and that is, what is the fastest route for me to get this packet that's living in Cambridge down to Johannesburg in South Africa, right? It knows the destination, it knows where it needs to go, but routing is about, how do I get there in the quickest way possible? Think GPS, right? Think GPS. This is about routing. This is what it's about. And there are a number of different protocols that are used to be able to do this. And they kind of fall into two kind of groups of protocols. The first one, we refer to it as IGP, Interior Gateway Protocols. So those are protocols that you would use within an organization. Think about Vodafone. Vodafone operates not only in the UK, but they operate in Portugal and Spain and in Germany, and it's one organization, or at least in name it's one organization, even though they're located in different countries, but that might all still be part of one autonomous system, even though located in different places, one autonomous system called Vodafone. So everything that they do, their routing protocols, they might have a group of routing protocols to manage their traffic, interior, inside their network. Now these could be something like RIP, OSPF, and we'll cover OSPF, ISIS, Cisco's IGRP, EIGRP. So there's a number of different protocols that would fall under, categorized as interior gateway protocols. But there's another bunch called exterior gateway protocols. These control the traffic that flows between autonomous systems. So within an autonomous system, IGP, between autonomous systems, EGP, okay? And one of the protocols, for example, that falls within the exterior gateway protocol is called BGP, Border Control Protocol. Think about countries, right? What happens when you go from the UK to Ireland? Well, you go through a border. What happens when you go from the UK to Germany? Well, you go through a border control. There's border control, correct? You go from here to South Africa, you have to go through a border control where they check your passports, etc., etc. So you get the difference between the two. Important to understand that. Now, one of the protocols that's really popular and very, very important to know is something called OSPF, and that simply stands for Open Shortest Path First, right? Open Shortest Path First. Makes sense. Again, think about GPS. GPS, open shortest path first. When you say, I want to go from Cambridge to Reading, you tell your GPS where you want to go, and it works out what is the shortest path. Now, it could be in kilometers or it could be in time. Many times it's in time. It will look at the two. So, well, if I'll weigh it time and I'll weigh it path, which is the better of the two? Well, if you have a priority for time, I'm going to give you the quickest link to get there. So you have these standards. Now, these things were developed 1987, roundabout there where OSPF was developed, and you have an open OSPF, and then you have an open system, and then you have the shortest path first, and that was an algorithm that was developed by a Dutch guy by the name of Edgar Dijkstra. Okay, in 1956, actually, 1956. And Dijkstra had a challenge, and the challenge was, how do you work out the shortest path between 2 points, right? And people say, oh, well, it's as the crow flies. Yes, sure. But when it comes to roads, it's not always as the crow flies, right? It's not quite like that. And you might say, oh, I know the road, I know the shortest path, I know that in my village from my home to the local supermarket, this is the shortest path. You know that because you might have driven it, you might have walked it, you might have cycled it. So in your head, you know that. But if you had an alien coming from outer space and, you wanted to explain to them, and they asked you, how did you work that out? You'd say, you just take this path. And why? Well, it's shortest. Well, how do you know? So he needed a mathematical way to describe this open shortest path algorithm, and this is what he's famous for. He developed a system. Now, I'd love to be able to show you Dijkstra's theorem in this lesson, but we just will not have enough time. So I'm going to create a bonus lesson, okay, where I'm going to show you with a practical example how Dijkstra's theorem works. And I'm actually going to make this something for your homework that you can work it out. I'll give you a whole lot of points and I'll say to you, using Dijkstra's theorem, go and work out what is the shortest path. It's fantastic. When you understand this, oh man, when I'm with my wife in the car and we go in somewhere, I'll type in, this is where we're going on my GPS, and my wife will often say, oh, I don't trust that thing, say to her, I do. It's like, how can you trust it? Because mathematically I understand how it works in the background, and it's a beautiful thing. But just for you, just so you know, that's the idea behind open shortest path first. It's what is the general direction that I'm going, and what is the shortest path that I can get there. Edgar Dijkstra was the Dutch scientist who invented that. So 1956. Now there's been improvements and things to Dijkstra, but fundamentally that's how it works. So the idea is OSPF helps us, and remember, all routers are going to have OSPF built into them. Okay, so it's a protocol that will be built into every router. They will know how to do this. And one of the great things about that is when you add another router into the network, onto the internet, OSPF will find out about that, and it will be very quick to adjust based on that. Say, there's a new router coming in. Cool. So now I have an extra route, and we're going to see just now how those things actually happen, because there's database changes that are going to happen. with OSPF, and there will be synchronization processes that will happen to allow this to happen for all the routers to be aware of something new that's happened, a new router, or maybe you took out a router, so we don't need this anymore, we took it out. When you take it out, the routers need to know, OSPF knows, that one is no longer there, so that no longer is part of our OSPF calculation. Okay, so here is, a general overview, very quick overview. This is not that bonus lesson I'm talking about. So here we have, three routers over here, and when these routers are switched on, etc., they're going to use the hello protocol. So just like when a new neighbor moves into the area, you might go to them with a piece of cake or something like that, or a cake, or invite them over for tea. Hello neighbor, how are you? Welcome to the area, etc. Routers kind of do the same thing, right? They use this protocol called the hello protocol, and they basically talk to each other. They talk to the router next door. So now I know my next door neighbor, my router next door, he's got 2 kids and he drives a blue car and he's a scientist. Hey, fantastic. I know that information, and they know I have, 3 kids, etc., and I got a silver car. Oh, fantastic. They know that information. And so I exchange information with the neighbor on this side, and I exchange with the neighbor on this side. They in turn exchange neighbor information with me and the neighbor on their side. So you can see how this thing is hierarchical, how all of these talk to each other, and that way they know and share information. So OSPF operations, they will have this what we call a link state advertisement. Okay, hey, I've got a new car. Hey, what color is your new car? My color is red. The car is red. Good. Isaac's got a new car. Our neighbor's got a new car, and his car is red. And on excuse me, I need to have some more of this. The neighbor on this side also knows that, and so we exchange this this link state. Okay, the state of the link. When something changes, we exchange this link state information. When we exchange this information, there are databases. So that's that LSDB link state database. Where are those databases? They are sitting on the routers. So when there is a change, when a new neighbor moves in, when a neighbor has another baby, and that information is shared with the neighbors, and the database is updated, right? Now, when the database is updated, there's new routes that are immediately calculated. So, okay, so now this changes that OSPF. If you come to me and what's the new shortest path? Well, when it's done all of those calculations, these databases spit out a route table. Remember, we spoke about route tables, I think it was in lesson 2 or lesson 3. So the route tables are updated, and now when somebody comes to me, when a packet comes to me and say, I need to go over there, I look at my route table, said, okay, let's work out the shortest path. I can connect to here, to there, to there, to there. I've got connections to all of these. It's a wonderful, simple, brilliant system that is used, and when these things work well, then we have access to any server in the entire universe, into the entire planet. Think about it. You could send an email to somebody on the International Space Station because of this enabling technology. Now, BGP, I once spoke to one of my colleagues from Bell Labs when I worked at Nokia, and I said to him, can you explain BGP to me? And he looked at me with a very serious face. This was at a restaurant, and he said to me, BGP is a bucket of hurt. I said, what do you mean? He said, this is a great protocol. It controls traffic between AS's autonomous systems. You can dedicate your life to BGP. The important thing I need to tell you over here is its main purpose is to exchange data between autonomous systems, to transfer, to push data, between one autonomous system and another. Now, TCP/IP, we kind of I've spoken already about this, right? This is that common language that all of these routers, all of these switches, the whole internet has to understand. As long as the devices talk TCP/IP, they can talk to each other, right? So we know about that. It's the world standard. Now we know it's not a protocol. TCP/IP, transmission control protocol / internet protocol. They are protocols, but in reality they are stacks of protocols. They are protocol stacks, a whole number. They are made up of a lot of different protocols, and they were invented around 1960. Certainly many of them were invented around that time for the Department of Defense. The idea, and you can see the idea over here, is the US Department of Defense had a problem. They were thinking, you know, if we are hit with a nuclear weapon, it could knock out our ability to retaliate, right? Because it would knock out our communication, especially if someone hit a particular data center or communication center. So we need to have a system that if one arm of it is cut off, it still can communicate. The president or the chief of the army or whatever could still go and press that red button. Why? Because there's no single point of failure. So that was kind of the thinking, and it really was brilliant thinking, and all based around the OSI model. So let's look quickly on the screen over here. Remember the 7-layer OSI, and next to it the more simplified, what we call TCP layer, which is TCP model, which contains the 4 layers. Just, it's not 4 completely different layers. It's just taking some of those layer 7 layers in the OSI model and kind of merging them together where it makes sense. Okay, so quite easy to understand. Now, if you look over here, you'll see on the network layer in TCP, there you get, Ethernet 802.3, and then we saw in the previous session 802.11. Remember 802.11 BGNACAX? Yeah, that's on that layer in TCP on the network layer. Above that we have IP, Internet Protocol, and in there you have other protocols like ARP. ARP is one of those protocols that works on the internet layer. Okay, it's not the only one, but it works on the internet layer. Then on the transport layer, TCP, for example, TCP on the transport layer. Remember, it could be TCP, it could be UDP. And on the application layer, HTTP, web, Telnet, POP3, Post Office Protocol, Simple Mail Protocol, FTP, DNS. Okay, UDP, we know about UDP, right? TCP, Directed Connection Protocol, UDP Connection List, just talks. Those types of protocols, well, DNS, SNMP, DHCP, RIP, yes, and ICMP again on the IP. And then over here you have tools, protocols like ping, or tools like ping and traceroute, etc. And they work on this application. They are application tools that use the ICMP protocol, for example. So there you see the difference between both. Now, in your home, you're not going to have the ISP is going to be an autonomous system, and they're going to allocate you an address within their autonomous system. So that black box that you have, remember, it has an internal address and an external address. The ISP will give you that external address. They will give you that external, and internally that box will generate its own internal one, right? And when you want to send data, we've looked already at this, you're going to have a device with an address 213, right? The origin address 210.213. it works out what the destination address is. Yes, the destination address, the Instagram server, that's its destination address. Source port, so source address, destination address, source port, destination port. 443. Do you remember what 443 is? HTTPS. That's the Instagram server, right? And so over here, there we go. That's what we want to do. When it gets to that side of the network, it goes through the gateway, right? Through the gateway, it gets to the destination. And then once it's got to the destination, it then needs to come back that way again. So you'll see how it goes from the device to the gateway, from the gateway to the destination server, to a specific port, and from there it goes back to the external address of the gateway, from the gateway external to the internal address, and then from there back to the client. Once it gets back to the client, it does that by talking to the port number, so the port, the origin port, the source port, that's the port that it will need to get back to. Okay, so we use port address translation to do that information to come back to the correct port, which is the application that actually opened that up. So we kind of understand how that works, and so you could have one device. So NAT, network address translation, means you could have one box, one black box, and behind that black box you could have hundreds, literally hundreds of devices that use internal addresses, but you only need one address on that box. So the packet is going to come in from the outside, is going to hit the external address, one address, and then NAT, this a network address translation and port address translation, is going to mean, I can go to each one of those devices, and within those devices I can send them to specific ports, which are the applications that made the request or that sent out that request, right? Here's an Instagram photo, let me say post. That goes out, comes back, acknowledges on that particular port. It's a really simple system that is used to be able to get information out. So even though these devices internally, they don't have addresses, when you have like a 192.168.0 whatever address, that address is not permitted on the internet. That's not the address that goes out. It's the address of the external address given by your AS, by your ISP, to that block, to that black box. That's the address that goes out. Now, I'm not going to talk much about security in this lesson over here, because I think it's in the next one. I'm going to talk a little bit, probably about half an hour, about security. It is really important, but security is a complex topic and it involves all sorts of things. They normally say that your weakest link in any system is always the human, right? You can have an expensive firewall, you can have standards, you can have, a password. Say you got to have a 20-digit password, you got to change that password every week. You can have all of that. But if somebody phones and says, "What's your password?" I say, who is this? This is the IT people. Here's my password. You are the weakest link. So security is an interesting thing, but to have a secure system, it's very difficult, it's complex, and you need to have you need to secure everything along that chain to be able to have a secure connection. And generally speaking, the big providers like Google and Instagram, all of them, they will force you to connect to them securely using HTTPS. But okay, So we've got all of that. TCP IP. What are the protocols that we use for communication? We've touched a little bit on this. The first one, of course, is if you look at this example, right? I'm wireless. I'm sending 802.11 frames to my AP. My AP is connected using a cable to a switch, to my little, to a switch that I might have in my office or in my house. That switch might be connected to the gateway using an Ethernet cable. Almost certainly is. Sometimes in home situations, this gateway is connected or is part of the switch. So these two devices are one device. Okay, that's often the case. We know that that's the internet. How do I get there? Well, we know that the first protocol that we need to use is DNS, the domain name service. And if you haven't watched it yet, please go and check the video. It's on Vimeo. There is a video there that talks about why my mother is better than the best DNS server. That explains DNS. That explains how when your computer needs to communicate, it can't do it Instagram.com. It doesn't know who it is. It needs to resolve Instagram.com to a IP address. Very much like when you need to make a phone call to somebody, you can't just say, phone, and on your phone you've got a contact but you don't have a phone number for them. Well, it doesn't work that way. You either need a phone number or you need an email address for them, or something that they can connect to, that your computer can connect to. So the first step, the first procedure when you try and send something is to use DNS. This is one of the fundamental protocols that you use for TCP IP to work. You need this. Now, this will connect you to websites, to email, to FTP when you want to upload a large file. And you're going to hear people talk about different terminology within DNS. They're going to talk about the DNS components. And these are going to be things like the namespace, extremenetworks.com, the namespace. They're going to talk about resource records. The most popular one that you'll hear people talk about would be an A record. An A record is an internet address record, an IP address. It's called an A record, right? And there's different types of records. There's mail records and internet records. There's a whole lot of different one of them. When we talk about DNS, you'll hear people talk about name servers, right? This is that program, that software that stores information regarding a domain. You're going to hear about Resolver. This is a program that extracts IP address from the server. So you go to the server, the DNS server, and the resolver says, okay, so what is the IP address for this domain, extremenetworks.com, right? And the resolver is going to give you that information. Once you have that actual IP address that the DNS protocol has given back to you, then this is the type of thing that can happen. Source IP, destination IP, source port, destination port. You can see over here I'm 10.213. You can see my gateway. We know the destination, what that is, but we have to go through our particular gateway. And what happens when we go through the gateway, you can see this beautiful animation over here. I'm going to go through these different autonomous systems, right? These different routers linked to these autonomous systems until I get out on Instagram. And the magic happens. That post appears. Really, really interesting. So that's one of the protocols. One of the other things that we're all familiar with is WWW, right? The World Wide Web. Invented by Sir Tim Berners-Lee around 1989. Unfortunately, he wasn't from Cambridge. He came from Oxford. But okay, yeah, it's our sister university, I suppose. But Sir Tim Berners-Lee, he invented the internet, the World Wide Web, not the internet, let's call it the World Wide Web. And this is what people like you and myself are very familiar with. There are people who think the internet is the World Wide Web. No, it isn't. The World Wide Web is just one of the services that run on top of the internet, just like email, just like FTP. Those are services that run on top of the internet. Now, www, we know that we use browsers, Chrome, Safari. No one uses Internet Explorer anymore, but whichever one Microsoft has, there's a whole a ton of these, all right? And we use them for web pages, for media files, for documents, for all sorts of stuff, right? And these are resources. We access them. We call these resources. We access resources using a URL. Right, a URL, a uniform resource locator. We have names for absolutely everything. And the URL is an object that specifies a location of a particular resource and the way that it can be reached. And that's why we do something like this. Let's take a look at these two over here. Now, you can see these are kind of familiar. Maybe not this, in itself. Maybe you've never seen that before. But the format of this should be familiar to you. Maybe this one, not so much. It doesn't matter. Let's try and understand what this is. So this entire thing we would call a URL. This uniform resource locator. That's what it's called, okay? That entire thing. Same over here. This one, this whole piece is the URL. If we break it down, then this part, the first part over here, is the protocol. Remember, HTTP protocol? That's what it is. That's how we address that protocol. If I go back here, here's the protocol. The protocol I'm using here is FTP. What is FTP? File Transfer Protocol. If you use a tool like Dropbox, you are dropping a file onto a web location, a Dropbox. That's using FTP, File Transfer Protocol. That's what it is. What's the next part? Well, this part over here, this part here is the host name, the machine name, if you want to call it that. Sometimes it's www. That's the host name. Here, what's the host name? Well, my server 1. That's the host name. What's the next part? The next part is somepage.com or local.local. That is the domain name. extremenetworks.com, ibm.com, nandos.com, right? That's the domain name. And this, what on earth is that? What's that? That is the fully qualified domain name. That's what it stands for. FQDN, fully qualified domain name. And that is this part over here. Okay, that is the fully qualified domain name. It might appear in an exam question. Web protocols, HTTP, you've all seen this. The default port for HTTP is port 80. All traffic travels over port 80. A client, what's a client? It could be your mobile device. It could be, a laptop computer, desktop computer. That's your client. A user agent, another term. What's a user agent? Well, when you connect to a website, your device, your phone, your tablet, whatever it is, has a user agent, okay? A user agent is like an identifier that tells the website, hey, I'm connecting to you and I'm a white iPhone 64 gig, this model, generation 8 or generation 9, or I'm coming to you from this browser or whatever it might be, but it gives you information. I'm a IoT device. So on the web server logs, you can see, how many mobile devices connected, how many desktop devices connected, how many people came from Apple, how many people came from Linux, how many people came from Microsoft. User agent. Server, Well, a server is the web server that accepts those HTTP requests, right? When you hit extremenetworks.com, it's a web server that responds. What about the next one, HTTPS? Well, same thing as HTTP, but it is secure, right? So that's what you expect to see when you connect to Gmail or to your bank or to your credit card company. That's what you expect to see, HTTPS secure. And the security is provided by a transport layer security called TLS. You used to do it using SSL, but nowadays, no, not so much. It's TLS. That's what we use, secure, to make that communication secure. And it uses security by using things like certificates, etc., etc. That's why when you connect to an HTTPS server like your bank, you will generally see a little certificate down the bottom. And if someone tries to impersonate that, your browser is going to say, whoa, whoa, whoa. This browser, this website says they HSBC Bank, but I don't think so because that certificate doesn't match. By the way, HTTPS uses port 443. That's the port that the default port that it uses. File transfer protocols. This is what I mentioned to you, like the Dropbox. You can have FTP protocols to. This is generally how you would also upload information to websites. If any of you keep websites or develop websites, when you have a website, you do an update and you upload it, it goes using FTP. You can also get SFTP, which means a secure file transfer protocol. You have protocols, all of these TCP/IP protocols for mail. SMTP, Simple Mail Transfer Protocol, to send mail, and then to go and fetch email, it will use Post Office Protocol. Okay, that's what it would use to go and fetch mail. Version 3 is kind of the latest. Then ICMP, Internet Control Message Protocol. This is one that most people are aware of. Most people in IT would know about this one and use this one quite regularly. Great for troubleshooting. This is that one that I said to you earlier that we'll cover. And it's really a protocol, very simple protocol, but that allows a receiving device like a server, for example, to report errors to you. Okay, it uses Internet Protocol as the underlying protocol, of course. There were 11 different messages originally defined, but the most recognizable is what we call an echo and an echo reply. So there's a tool that we use. We call it Ping. You might have heard of it, PING, right? This is the most common implementation of this protocol, ICMP. When you hear ICMP, Ping, and think about it. When you go play golf, if you use the equipment Ping, when you hit that ball, it makes like this ping sound, ping, right? That's how they came up with the name Ping, right? The ICMP kind of does the same thing on the internet. You ping a remote host, a remote device, to see if it's there. If somebody sets up a printer in your office, once they've set it up, they want to make sure it works. So when they set it up, they would have given it an IP address, or the DHCP protocol would have given it an address, and they would have pressed a few buttons on the printer, and it would have printed out the page, and it would say on that page, the IP address is this, ABC, whatever it might be. You then go to a computer, you sit down on the computer, you run the ping command, and you say, ping this address. And what it's going to do is it's going to send a number of packets. In Windows, it's 4 packets. It goes ping, ping, and it listens for the echo. Ping, ping, ping. When it gets an echo, it knows, that printer is there, it's responding. So that's how network engineers can figure out if things are up or down. They can sit in an office and they can ping a server in the US. Is that so? Why isn't the mail working? Ping the mail server. Ping, IP address of the mail server, and if the mail server is up, it will respond. Yes? Now, not all devices respond. They should, but not all of them. Sometimes people just say, well, you know what? Everybody wants to hit my server to test. I'm just going to turn off, when people ping me, I'm not going to respond to them. And it might appear that that server isn't there. It's not that it isn't there. It's just that they have turned off the responses. They've been bad, but I mean, if you Google, you must get a lot of pings because everybody wants to do a ping. Let me show you what it looks like. If you're on Windows, you can do that right now. Just go to next to your start button, just type in CMD, which brings up the command prompt. On Mac, it's just type in, press command space and then type in terminal, and you have this black DOS window kind of that opens up. And you can do something like this. In Windows, you just go ping space google.com. And you're going to find something like this. It's going to say, I'm going to be pinging google.com. This is the IP address. I did a DNS resolution on there. I found that that's the address. I'm going to ping it with 32 bytes of data. And by default, Windows sends you 4 pings, sends out 4 pings. There we go. There's the echo. It sent an echo and it got an echo reply. Right there it is. I sent 32. Sorry, there I sent 32. I got it back. It took me 44 milliseconds. Total time to live. How long did it take me? 119 milliseconds. Look, 4. This is a fantastic connection. I sent 4 packets. I received 4. 0% loss. We're happy with that. Approximate round trip time in milliseconds, minimum 44, maximum 57. That one there, average 51 milliseconds. What a fantastic tool. So give it a go. After this, just write down that command and afterwards go and try that out. Give it a go if you've never done one of these before. That's ICMP and ping. But there's another one. There's another one that we can use, and that's called traceroute. So in Windows, it's called tracert. So it's trace RT. So it sounds like tracert, right? In Mac, it's traceroute, one word. So traceroute shows you the path that packet goes. So when you say you've just done a ping to Google and you're going to wait and you're going to get a response from Google, and you can also use traceroute to say, okay, let me see the path that it took to get there, to get to that. And the way that it uses a ping, but it gives it, when it sends out this traceroute command, it gives that ping a time to live of 1 second. So it goes out, it gets to the first router, and the first router says, oh, hang on, your time to live is now over. It was only 1 second. Sorry, go back. That means first router is working. Now it goes again, but this time it gives it a time to live of 2. So it goes to the first one and the second one, and gets to the second one, says, oh, you don't have any more, you have to go back. Goes back, now sends it to 3. And so it tracks the route. So if you want to see how your machine ends up at google.com, you use a traceroute, and that shows you the route that packet follows. Here's an example. Trace RT, remember, Mac trace route, one word, but trace it google.com, and look at what happens. It says, okay, it's resolved that to that address. I'm going to do it a maximum of 30 hops so that I don't keep hopping all the time. There's 30 hops. And it's, see, there I go, hop 1. Now that is generally your gateway, your little black box at home. There we go. And then from there, it starts going to the different locations. Look here. Here it's got the name, the DNS name, plus the IP address of where it's going to. So you go down by 8 hops. It finished and it came back. Hey, I've reached Google. That's the route that I took to Google. Now, if you do this in Mac, and I think at Windows as well, but I know in Mac, if you do trace route space -a google.com, it will actually show you the autonomous systems as it goes along the way. It's absolutely fantastic. So this might also appear in the exam. Anyway, enjoy that, write that down, go and play with it. I will have homework for you, so please, the homework will be on the Meeting Pulse app. We've been pushing this URL all the time, showing you where to go for. Please follow that URL that's been in the QR code, because that's where you're going to be finding the homework for this week. Also, make sure you watch the homework for last week, session 4. It was an animation of how the handshaking protocol happens. Fantastic, best animation I've ever seen to help you. I'm sorry we ran a little bit over time on this one, but I hope you've enjoyed it. I hope that you've learned a lot and you understand a little bit more about wireless and a little bit more about autonomous systems and the way the internet works. Cheers, ciao for now, see you next week.